start करते हैं. Bismillahirrahmanirrahim. So today's tech talk is about GenAI, जो आजकल का सबसे बड़ा buzzword है. What we're trying to do is make it focused on the development side of the work, not the tool side. Normally आप काफ़ी सारी talks होती हैं आजकल मिलते हैं जो कि बता रही होती हैं GenAI को आप अपनी ज़िंदगी में पर्याप्त बनाने के लिए या whatever करने के लिए कैसे यूज़ कर सकते हैं और whatever else there are practical applications or uses of GenAI. What we wanted to do with Dr. Zainab today was to focus on going deep into the development life cycle of GenAI LLM-based development. Right? And what that means is कि जो आपकी सतही लेवल पे जो APIs आपको मिलती हैं उस पर आप एक बेसिक चैट इंटरफेस तो कर सकते हैं, लेकिन अगर आपने इसको डेवलपमेंट वर्क को नेक्स्ट लेवल पे लेके जाने हैं, यू वांट टू बी एबल टू डू मोर एडवांस्ड यूज केसेस जो कि आपके वनीला नहीं हो सकता, तो what are the areas and what needs to be built around a GenAI service to build what's the next generation of software solutions that are going to be built forward. So understanding that and to taxonomize and put that into a framework hopefully easy to digest. I know we were 5 minutes of time, but the content is so इसमें से काफ़ी सारी चीज़ें थोड़ी easy नहीं होंगी, लेकिन I would encourage the people, especially the developers over here, to ask questions around okay अच्छा कैसे हो सकता है, क्या करना होगा, इससे क्या होना होगा, because the hope is if you understand that, then we can build the next generation of applications using LLM capabilities like LLMs. All right. Welcome back to the tech talk.
Thank you. Assalamu alaikum. So it's a pleasure to be here. Thank you for coming. So I'm Zainab, as you already know. I'm a senior ML AI scientist here. Before that, my background is in academia. I have a PhD from the University of New South Wales in cybersecurity and partially in machine learning. And before this, I was teaching at FAST for 3 years. All right. Generative AI is an exciting area to be in right now. I feel very fortunate to be working in it. We've all seen how lots of new tools and technologies are coming out. Lots of new things are being made possible. So in this talk, we're going to focus on large language models, LLMs for short. And we're going to see what is possible, what it is becoming now possible to achieve with them, and how you can get the most out of them in application use cases. All right. So, not sure why that's not working. All right, so we'll start with the introduction, which is the what and why of GenAI and LLMs. That's basically an introduction to the area. We'll then go into the how, which is the LLM service development lifecycle. I'll talk more about it when we get there. That's the main section of the development. And then eventually we'll talk about the future, which is building GenAI agents. This stopped working, so I'll just use this. This is not working. All right, so what is GenAI? I'm sure we already know, but just so that we're on the same page. We know that traditionally we've seen AI, over the last 10, 15 years, we've seen AI algorithms making predictions or decisions, based on given data. And that's what's known traditionally as discriminative AI, where it looks at given data and it makes decisions about it, or it predicts future. Yes? I think I'm supposed to be muted from here. It's fine, right?
She's got this mic?
Yeah, I've got this mic. I think this is the one that's connected. Yeah, should be all right.
Oh, but a lot of people have joined on Zoom as well. You can Zoom connectivity of it. Okay, just tell people on Zoom
All right. Sure. Still not working. I tried to fix this, but anyway. OK. So what is, as I was saying, discriminative AI is the more traditional realm of AI where, algorithms make predictions or decisions that are based on given data that the algorithm has seen in the training. Generative AI is a completely new class of algorithms that can generate new content similar to the content that it's seen in training. This visual will sum it up nicely. If you give a discriminative model, that's the traditional type of AI that we had before, a picture of a dog, maybe it will classify it as a cat or a dog. So it will output cat or dog, a label, right? A generative model will take a picture of a dog or a picture of a dog, and then it might generate a new picture, an original picture that it has not seen before, that maybe nobody has seen before, right? So that's the difference between generative and discriminative AI. Now, what are large language models? In general, generative AI can apply to any sort of data, right? So you can generate images or video or audio or text. The text part of that is the focus of large language models, right? The focus is on text. So I'm pretty sure everybody knows what an LLM is, but I'll still define it just so that we're on the same page. So it's an AI algorithm, essentially, that's capable of generating new textual content. For example, original stories or answers to questions and lots of other things. Thanks to OpenAI's ChatGPT, we've all had experience with at least one LLM, right? Even if we're not working in that area. So, and the first time that you use it, it's really quite magical, right? It really feels like there's a bit of magic. How can it do it? So what really is the magic? That's what we're attempting to unpack here. If you sum it up, the magic is essentially two things: a very large number of trainable parameters and a very large amount of training data. Now, we know generally in machine learning, who's familiar with machine learning, that if you add more and more parameters to a machine learning model, it's able to do more and more complex tasks, right? It's able to learn more complex ideas. So with a large language model, you have a very large number of trainable parameters. And then when you train it with a proportionally large amount of training data, that's where it shows that magical behavior that we see with ChatGPT. And how large is large? Just to put that into perspective, it goes up to billions and even trillions of parameters, right? Palm is a very large language model that has 540 billion parameters. GPT-4, I believe, is said to have around 1 trillion parameters. So that's the large in large language models. So that's where the magic comes in. So let's talk a bit about how LLMs are built, right? So LLMs basically go through a two-stage training process to be able to do what they do. The first stage is called pre-training. This is where you feed in vast amounts of unstructured textual data, unstructured text. And the outcome of that is a model that's able to look at a sequence of words and predict the next word. And I'll show you exactly how that works in a minute. And then this is not enough for it to be able to actually carry out instructions. So it goes through a second stage of training, this time on a small amount of data, where you give it some task-specific data set, so specific to the task that you want it to do, and you tune it on that. And as a result of that, it's able to follow instructions. So we'll talk in more detail about these, both of these stages. So as I said, the first stage, which is pre-training, the outcome of that stage is next word prediction. So if you feed into a model, the boy went to the, it'll output the next word. And the way it does that is essentially it builds a probability distribution over its entire vocabulary. Right? So if we assume that the entire vocabulary of the LLM is these 5 words, in reality, it's much higher, right? It's 20,000 to 50,000. But if we assume that's all there is, you can see that it's built a probability distribution over them, right? It's given these different probabilities to different words, and it's going to output one of the words with a higher probability, not always the highest, right? It's kind of an oversimplification to say that always the highest probability is chosen, and we'll go deeper into that idea also later. But if we assume for now that it always chooses the highest word, so it's going to choose the boy to go on with. This is what it's already able to do with just the first stage of training. Okay? It's able to output the next most likely word. So as I said, if you say boy went to the, it can very confidently say park, and it'll make a sensible guess most of the time. But if you tell this same LLM, write a story for a 5-year-old with dinosaurs, astronauts, and a black hole, real prompt given by my 5-year-old, it might not give you, it actually definitely will not give you what you wanted. It might say galaxy, it might say universe, right? It's just giving you the next word, because that's all it's able to do. So from stage 1 of training, which is pre-training, it's not yet able to follow instructions like these. It's not able to summarize the following passage, analyze the given data, classify the following review, things that we instruction different kind of data set. Now we're not giving it unstructured text anymore. Now we're giving it specific prompt completion pairs. So we're showing it lots of examples of what we wanted to do. So for summarization, maybe we'll give it passages, long passages, right, or long articles, and we'll say summarize the following into 300 words. And then we'll give it the answer as well. So lots of pairs like that, of prompts and answers, right? And from that data, it actually learns what we want it to do when we give it an instruction like that. For multitask tuning, you would give it lots of these data sets, each one specific to a different task. One for summarization, one for story writing, one for question answering, and so on, okay? And these are, although these are still large data sets, so for example, this could be maybe 100,000 examples or a few 100,000, that's still a lot less than the original pre-training data, right? So this is much faster and cheaper to do this stage. At the end, you get out an LLM. It says fine-tuned LLM over here. The terminology in this field, being a new field, is a little bit fluid still. I find that fine-tuning, the term tends to get a little bit confusing, so I prefer to say instruction-tuned over here. So this is an instruction-tuned LLM. Fine-tuning is of different types. Instruction-tuning is just one type, okay? So this is an instruction-tuned LLM that we get out of here, and now it's able to follow instructions. All right. Now, given that you have an LLM that's able to understand human language and that's able to follow instruction that it's been trained on, and given that we've got LLMs like GPT-4 that are able to carry out all sorts of instructions, can we say that we can always just use an existing LLM for all of our use cases? What do you think? Probably not, right? Actually, so let's see why not. That's because, one, an existing LLM capability might not match your use case, because your use case might be very domain specific, or it might be very specific to even your own company or your own data. For example, I might want it to pick out anomalies from a security tool's log file, and it's never seen that security tool, and it's never seen those abbreviations and that jargon, and it doesn't know what a normal event versus an abnormal event looks like, right? So it's not able to do that. Secondly, even if it is able to do that, maybe only very expensive LLMs are able to do that, right? That are too expensive for me to use, or they're too big for me to host, right? So that's why an existing LLM might not always be suitable. Now, generally in machine learning, what we do when a model is not suitable, we train our own model, right? So just to get that out of the way, do you think we can train our own LLM? Most of us cannot, because training costs are prohibitive. Training costs are very, very high. Llama is a model from Meta that has a few different variants. The 65 billion parameter variant of Llama. Now, 65 billion for a large language model is like medium-sized, right? It's not the largest possible language model. The authors report that they ran a training data set that was about 4.6 terabytes for 21 days on 2,048 GPUs, right? So I've just taken the reference, just as an example, pricing from Google Cloud. If you add that up, that comes to over $4 million. That's for training a medium-sized LLM, and 4.6 terabytes is not the biggest data set either, right? So the costs really add up for pre-training. So most of us cannot pre-train our own LLM. So now you can't use an existing LLM, right? Yeah.
Exactly the parameter. If you're looking at an article, is a word a parameter?
No. So a parameter for a machine learning. So a machine learning model is basically made of lots of different units that carry weights, right? So specifically for an LLM, if you go, because we skipped the architecture bit, so maybe it's not clear. If you look at the architecture, it's made up of a bunch of neural network-like units, right? A neural network is basically, it's like a graph, right? It's got nodes and edges. And those edges have weights, right? So parameters are essentially weights of the model. So when we say 65 billion parameters, it means we have that many edges connecting a large number of nodes, right? And so you have to train all of those parameters because an example will go through the network, yes?
65 billion edges or nodes?
65 billion edges, yeah, edges. Because edges have weights. Yes, yes, yes. And there are other parameters. The edges are not the, so 65 billion edges plus some other parameters also. It's not just edges, but most of the weights do come from the edges.
Maybe one way to look at parameters is, these are the matrices for which we need to find the values.
Yes,
And
exactly.
they are the matrices all combined, they are 65 billion.
Yes, there's a matrix that's representing the whole architecture. That's right. Thank you. All right, so now given that you can't train your own and an existing one might not be matching your use case, what do? The best option that most people use is to choose an existing LLM, right, that's been pre-trained, that's been instruction tuned, and you adapt it to your own use case, okay? Now, that's what we're going to talk about in the how portion of this talk. We're going to talk about the LLM service development lifecycle, which is where we take this issue of, I've got a use case, how do I go from there to deploying an LLM that meets my needs, okay? So the LLM service development lifecycle, again, these steps are not set in stone yet because it's a relatively new field, but this has emerged over the last couple of years as a kind of standard set of steps that you follow when you've got a use case and you need to deploy an LLM that serves that need, okay? So you start from specifying your use case like you would for any project. You choose an LLM, an existing LLM. These are called foundational models for that reason because these are already available and you choose it for your use case according to that. And then you adapt that using several techniques that we'll talk about. In fact, that's the major portion of this talk. And now when you've adapted it, then you have to evaluate whether it's meeting the need or not, and then you would deploy it. So we'll start with the step of choosing the LLM because so the use case will assume that you've already thought of your use case, right? So you could have any number of use cases. So now that you have a use case in mind, how do you go about choosing your LLM? All right, there's a lot of detail here, and we'll unpack it slowly over the next few minutes. Basically, choosing an LLM once you have a use case is contingent on these 4 factors primarily, right? One is what use cases it's already suitable for out of the box. Okay, that depends on a couple of factors that we'll go through in a minute. What is the size of the LLM that you need for your use case? So the size is in terms of the number of parameters. Whether it's open source or closed source, right? What is the access? And then what context is it able to look at? You would consider all of these factors when choosing your LLM. So let's look at each of these one by one. If you Google LLM use cases, you'll see lots of figures like these pop up, right? Some of these are from research papers, some are from blogs where people have run their own experimentation on different models and then plotted the results for which tasks are done well by which LLM. For this particular figure, the darker green represents the LLM being good at one of these use cases. So right there, you've got models. I'll just turn on the pointer for a moment. Unfortunately, the device is not working. All right, so these are different LLMs, and these are different use cases right here. Okay, so the darker green shows which LLMs are better. So GPT 3.5, for example, you can see is better at most of these things than the other models. Which model is better at what? That depends primarily on 2 things. One is its architecture, and we haven't gone into architecture because of lack of time, but there are primarily 3 kinds of LLM architecture: encoder only, encoder decoder, and decoder only, and these are suitable for different kinds of jobs, right? Most LLMs that we see available, foundational models, they are decoder only architectures because it's a versatile architecture and it's good for many different kinds of tasks, right? So that's why you see that most of these are green in most areas. The second thing, as you can see, this is a decoder-only architecture, but it can only do one thing. That's because it's only been tuned for this one task, right? So that's the second reason. One is the architecture. The second is what sort of tuning instruction tuning, it's already seen, okay? So based on that, different LLMs are good at different things. So that's the first thing that you would probably consider. Like if you had a classification task, you would just go with one of these encoder-only models because these are small, these are lightweight, and they're quick to run for just classification. But you have a more complex task, you would go with one of these at the bottom. So that's the first thing. The second thing you would, as I said, you would choose based on size. Now, this is a figure that's representing model sizes over time. So you can see that bigger and bigger models have been developed with time. So this is 2023 here, right? So you can see that we're going into between 100 billion and a trillion parameters. The axis is, I think, log scaled. Right, so in general, larger size represents, as we already discussed, more complex tasks. So if you have a more complex task for the LLM to perform, you would generally go with a larger model, right? And if you have a simpler task, you could go with a smaller model. Some people have talked about a new Moore's law for LLMs. It's not quite a Moore's law because you can see that smaller models are still being developed, right? So smaller models still have their place because there are certain simpler tasks for which a smaller model will do perfectly well, right? So then you don't need to use a large model that has a higher cost, higher computational complexity and everything. So you would choose a model in accordance with the requirements of your task. Then for open source versus choosing between open and closed source models, in general, open source LLMs, they have lower cost because you're not paying a per token usage cost, right, as you do with closed source. What I mean by closed source LLMs is LLMs that are just hosted behind APIs and you can't actually access the model. Open source, they are available. The whole model with its weights, with its source code is available. So you can just download it, do whatever you like with it, right? So for open source, usually...
A quick question on that.
Yes.
What does it mean in terms of size, storage, and compute to host, let's say, a mid-size LLM model?
So, I mean, it's your own model, so you would host it somewhere, right? You would need to pay a hosting cost. And then there's a computation cost because it's a very large model. There's a memory cost, first of all. You have to store all those 65 billion or whatever parameters somewhere. And then there's an inference cost. At inference time, you're doing all of that computation because your example is then going through the entire network, right? So,
okay, so you may not have
so it's not free,
but I think it would be useful to see maybe in a subsequent presentation to see some quantification of
right, of the comparison. Yeah, makes sense, sure. Okay, so one, in general, open source LLMs will cost lower because the closed source ones will charge you per token. Token is like 3/4 of a word. We use that pretty often in LLMs. Token is like a word in LLM vocabulary, right? So roughly you can think of them as words. So there's a per token cost of usage there. With open source, you can, obviously there are much more adaptation options. Closed source LLMs, they only expose some part of the LLM for adaptation. So there are usually very, very limited options. We haven't quite seen what adaptation means yet. That's going to come up, but you have much more flexibility here. Your data remains private with an open source LLM. With a closed source LLM, you're sending it to some external model. However, accuracy can be lower often for open source LLMs. Oftentimes, the closed source ones are performing much better. And then also you need much more technical expertise to locally deploy a model and manage it. Closed source ones are much easier to use. So again, based on your specific requirements, you would make a choice here. The final thing that you would choose on is the context window length. And an LLM, anyone who's used an LLM would be familiar with this. An LLM is able to look at a specific size of data when it's making the inference, when it's replying to your prompt. It's able to look at a certain size of data. So different LLMs have different context window sizes. So if you needed to be able to take a lot of information into account, you would choose one with a larger context window. Context windows have been increasing with time. I think the latest, the largest as of now is 128K tokens, right? So it's quite a large context window that's available now. But obviously, if you're using a larger context, you also have increased latency and a higher inference cost, right?
Context window is also measured in the number of tokens.
In number of tokens, yes, yes.
Excuse me. So one question here: where do the vector embeddings come in all of this?
We will get to that in a bit. Yes, that's coming up as part of the adaptation options. All right, but just to just to answer that maybe briefly right now and later go to the detail. LLMs actually represent text as vector embeddings. Vector embeddings is a numerical representation of text. So when you input text to the LLM, it doesn't just consider the words. It actually embeds that into a vector first, into a vector representation, and then it does all of the processing on that. And in the end, it converts it back into words. Okay. All right. So we saw four different factors on which we base the choice of our LLM. Now that you've chosen your LLM, right? So say you decide to go with some open source model. Now you need to adapt it to your use case. Adaptation basically means you want to get the most out of it, right? So you want to tweak it and tune it and set the parameters such that you get the most out of it for your use case. So now we'll go into the details of how adaptation is done. So I'll explain these in the next slide. So just skip this from here. These are 5 different reasons that I thought of that you might want to adapt your model. This is not an exhaustive list, right? But these are most of the reasons that I could think of. One, you might want to give it a new task capability, right? Maybe it's not able to do something that you want it to be able to do, like that anomaly picking out of a security tools log file example. Then you might want to adapt it to a particular domain. LLMs are trained on general text, right? So it's not specialized for, say, the legal domain or the medical domain where you have very specialized terminology. You might want to do that. You might want to align it with human preferences. We'll see the details of that in a minute. Or you might want to just improve the inference, just structure the prompts in a way that it understands better, it's able to respond better. Or you might want to give it access to new knowledge, right? To new non-public knowledge because it's just trained on public knowledge. You might want to give it access to your own company's data, for example. So the first three goals of adaptation, these are accomplished through fine-tuning, which is basically when you're retraining the model, right? So you're doing this training process, you're changing the weights of the model. The last two can be accomplished without it, just by changing your prompts, just by changing what you input to the model, and you treat the model as a black box, and you don't touch the weights, you don't change it internally. So that's why usually people start here for when you're using an LLM, it's a good idea to start here because it's easier to do, right? Oftentimes, this will be enough. But if it's not, then you go on to the fine-tuning, or if you have a specific use for fine-tuning. All right. So let's go through these one by one. We'll look at different techniques for how you accomplish these goals. This one's the easiest, tuning for new tasks, because we've already seen this. This is basically exactly the same as the instruction tuning step that we saw in the LLM training, right? So you give it prompt completion pairs, and you let it learn how to do the task that you want it to do. Why would you do this when large models like GPT-4 can pretty much already do everything? Often it's to tune a smaller model. That's usually the most common reason for giving a new task capability. You might need to tune a smaller model that has a lower cost and that doesn't have that capability that you need it to have. Okay? So for example, if I say to GPT-4, grade my student's essay based on this criteria, it'll probably do a really good job, right? But if I give the same thing to a very simple model like BERT, which is one of the smaller models, it doesn't know how to do that by itself. But if I can train it, because BERT is good at classification and pretty much just classification, it'll learn really well how to do that, and it'll be much faster and cheaper to run, right? So that could be one of the main reasons that I want to tune for instruction for a particular task. Secondly, you might want to adapt to a particular domain, as I gave the example earlier of the medical or legal domain, where sometimes, especially in the legal domain, sometimes we see that words that we usually use in the English language are used, but they have a completely different meaning there. So you want the language model, if you're using it in that domain, you want it to be able to understand what that particular word means in that context. So then how that is done is this bit up here. This is just the pre-training stage. This is already done, right? We're not going to be doing this again. This is just training from the generic corpus. And then you additionally give it more from the same domain. So this is like the pre-training stage, essentially. You give it more unstructured data, but now you give it from that domain so that it learns the meaning of language in that domain. So you just train that model, and as the output, you get your domain-specific LLM, right?
So two questions actually. What's the difference between this step and the last step where you were doing the prompt engineering using the textual data? And the second question is, can you give some examples of parameters that might be passed in this particular case, let's say for medical or financial?
you would just, in this case, you would just pass it unstructured textual data. This is exactly the same as the pre-training stage of an LLM, where you're giving it lots and lots of just unstructured text and letting it figure out for itself what the words mean. This is exactly the same, except that you're taking a pre-trained model. Now it already knows, for example, the English language, but it doesn't know medical terminology or legal terminology. So you just give it unstructured legal documents, and you just let it learn, and generally it's going to learn, right? Bloomberg, I think. Bloom is a model that's been trained like this on financial data, and it's able to understand financial terminology. It's actually available for use. Could you repeat your first question again? I didn't understand.
Between this and the prompt engineering step number 5 that you showed in the previous
Prompt engineering, so here you're actually training the model. You're changing the weights of the model, right? It's a training process like we have in machine learning. Prompt engineering, you're just changing the input of the model at runtime. Like the model is already deployed. Now you're figuring out what input should I give it so that it performs best. Okay? Is that clear?
This is the fine-tuning part.
Yeah, this is fine-tuning.
Fine-tuning part of how fine-tuning can happen.
Yeah. So they're completely different mechanisms, yes. All right, the third reason that you might adapt is to align a model with human preferences. This is so important that it is actually now known as a standard part of making any LLM available for public release, right? So what could human alignment mean? For example, you might want to give the LLM human ethical values, right? So for example, you might want to discourage it to output hate speech from producing hate speech or like toxic responses. Or you might want to increase its helpfulness. We'll see an example of that in the next slide. You might want to discourage harmful responses. Like if I ask, how do I hack into my neighbor's Wi-Fi? It shouldn't give me the step-by-step, right? It should actually tell me that it's illegal, right? Similarly for other illegal things. Or you might want to train it for a particular speech style that you prefer in your use case. Like maybe I'm building an LLM for primary school students, so I want it to talk in a language that's suitable, or a formal language, or a technical terminology, things like that. So these are all human preferences that the LLM can't figure out on its own until I tell it, right, what I want from it. So for this, so just an example of an unhelpful and helpful response. For example, if I ask ChatGPT or any other LLM, I have a rash, runny nose, and a headache. I also see flashes of light. What could I have? Can you give me possible diagnosis? And it just tells me that I'm not a doctor. You should see a professional. That's not a very helpful response. Maybe in my use case, I have somebody using this who can already use this LLM responsibly, right? So maybe I wanted to give me a helpful response. That's possible diagnosis. So that's a human preference. The LLM doesn't know by itself. Both of the responses are valid, right, technically. It doesn't know what a human prefers, the first one or the second one. So I have to teach it that the second one is more helpful, okay? So the way we do that is through something called RLHF, reinforcement learning with human feedback, okay? It's a fairly complicated process, but I'll try to kind of cover the high-level idea of it over here. RLHF, and as I said, this is an essential part of now pretty much releasing any LLM. So the way it works is in 2 steps. In the first step, you train a machine learning model called the reward model to just be able to distinguish between a human preferred and a not preferred response, okay? So the way you do that is you give some prompts to your original LLM that is not human aligned yet, and you give it usually prompts that are likely to generate responses that are not human preferred. So you give it lots of those prompts, and you make it generate multiple responses. So now some of these responses will be human aligned, some of these will not be. You get a human labeler to actually rank these responses in order of preference. And based on that human labeling, you generate a data set that now can train this machine learning model. So now this model will, because it's seen lots of examples of prompts, LLM completions, and whether that completion was preferred by the human or not, it's now able to give rankings to LLM completions. It's now able to tell the LLM your completion is human preferred or your completion is not human preferred based on this training data that it's seen. Does that make sense so far? Often this reward model is also an LLM. Oh, sorry. All right. In the second step, you now tune the LLM by using this reward model. So you get the LLM, you feed it lots of new prompts now. This is a new training set. You get it to generate responses, right? And you feed each response to the reward model. Now the reward model, because it's learned to distinguish between aligned and unaligned responses, or preferred responses, not preferred responses, it's able to give a score to that response of the LLM, right? ideally a score that closely matches a score that a human would give. So higher score means that this was a good response. A lower score means this was a bad response or a response that a human would not prefer, right? And based on this score, you train the original LLM, right? You adjust its weights so that in future it's more likely to produce preferred responses and less likely to produce responses that are not preferred. The details of that training we're definitely going to skip. PPO is an algorithm that's a very popular choice for this. Recently, another approach has come out. Again, we can't go into that right now, but that actually makes the whole process much faster. It directly fine-tunes the original LLM and completely gets rid of the reward model. That's
one question.
Yes.
We've seen this very regularly with every ChatGPT response. There's a thumbs up, thumbs
yes.
down. Where does that fit in over there?
The thumbs up, thumbs down would fit into the human feedback over there. So they're basically using that thumbs up, thumbs down to generate this data. And then at some later stage, yes. Yes. Okay. So at some later stage, they're going to probably collect that data set, clean it, use it to train the reward model, right?
But before that, I mean, do they have an internal process where they get this human feedback? And I mean,
I would assume.
What I'm trying to understand is, there is perhaps an infinite number of prompts, and obviously there are more infinite number of responses.
Yes.
Right? And how do you define sufficiency that okay, we have enough human feedback incorporated into the model?
So I think there's a standard, I don't remember the number, but there's a standard number, it's like 50,000 or 100,000, something like that. That's sufficient for training the reward model. So that much is enough.
It's quasi-automated. These are the prompts and these are the possible answers that we would endorse. It's kind of automated.
Any humans?
RLHF is actually an actual human doing it.
Actual human.
Yeah. But what I was going to, yeah, that's a human. That's a human response.
But that's not reliable, right?
Over a large amount, they're assuming this aligns with what you
Yeah.
But you're right. I mean, if you feed into 5 people who are biased towards something,
yeah.
then you will get a bias in that one.
So I'm really glad that came up because that actually takes us to RLAIF. So some researchers have proposed RLAIF instead of RLHF. So replace the human with AI, exactly because the human may be biased, right? And secondly, because it's not scalable. So use an LLM over here to rank these responses instead of a human. That's the only difference. The entire process remains the same, but you replace the human with an LLM. And I think one research paper that I read showed that human-to-human agreement for such ranking is about 75 to 80%, while human-to-LLM agreement is about 80%. So that means humans and LLMs agree the same amount of time as humans and humans agree. So it's as reliable as using a human pretty much. Yes. So there are lots of different ways of doing this RLAIF, but it is possible and it is being used. All right, so that's the main idea of RLHF. So this is used if you want to adapt your model to human preferences. So now we're done with the fine-tuning, all the goals that are met by fine-tuning. As I said, where you would normally start is not fine-tuning because that's a harder process that involves training that usually requires at least one GPU, right? If maybe a few hours or a day or a couple of days on a GPU. Where most people would start would be just changing the input of the model, right? And there are two ways you can do that. You can just improve the inference by either tweaking some parameters that are generally exposed by LLM APIs. We'll go into those in a minute. Or you can tweak the prompt structure. It's been shown that just structuring the prompts differently in a way that's more understandable for the LLM can improve the output a lot. Okay? So we'll go into both of these now. I don't want to go into too much detail over here. It gets very mathematical, and I think we don't have that much time. But essentially, you'll see in most APIs 2 parameters, top K and temperature. Right? These are available in most APIs. They basically control how the LLM picks the next word from this probability distribution. We saw this probability distribution before, right? So the LLM has built this distribution, and now it needs to pick out a word. It can either just pick out the most likely word every time. The problem with that, it sounds very intuitive, but the problem with that is that it makes very static and unnatural sounding text in practice. So we want to give it some randomness. We don't want it to always just pick the most likely next word. But if we allow it too much randomness, then it could end up picking very unlikely words as well. Like hospital, in this case, has only a 5% chance. But it could, 5% of the time, it could pick hospital. So we don't want it to do that either. We want to give it some randomness, but we want to restrict that randomness also. So we use top k and temperature to restrict that randomness. Top k basically just gives it a number k and says just pick from these k choices, right? An alternate of that is top p, where you make this k dynamic, but I won't go into that right now. So it's just picking from the top few most likely tokens instead of just anywhere. And temperature basically works slightly differently, so we won't go into the details, but it computes a different probability distribution. The main thing to remember is that lower temperature means less randomness. Higher temperature means more randomness, right? So if you push the temperature up, it makes a more flat probability distribution, and it's more likely to get more creative, to pick more different words, right? So you can tweak these parameters, and generally any kind of tweaking that you do this very iteratively, and you see how your model is doing, right? So you'll keep changing these parameters, seeing how it is doing, yes?
About the temperature, is it, so if the higher the temperature, does it mean that the response is more creative, or is it just that, or is it also taking, let's say, more context, more data?
No, none of that. Yeah, it's just how it picks the word from this, really.
So basically,
So
basically, if we have a higher temperature, it means that the response would be from the reference. It might be paraphrased and more creative. There will be less,
less deterministic,
yeah,
less static,
exactly.
yes.
And that's it.
Yeah, that's it. Usually when we do experiments, we set the temperature to a lower value, like to 0 even, so that it comes up with the same response every time. So that's when we want to vary the response between runs. All right, and the next thing, as I said, after parameters, other than tweaking parameters, what you can do is actually change the structure of the prompt. There are some very well-known techniques that you can use to write better prompts. One of the very popular choices is in-context learning. This is where you are basically providing, as you can see, examples in the prompt itself of the task, right? So similar to how we provided prompt completion pairs in instruction tuning. Now we're not tuning the model, we're just giving it a prompt, but we're showing it at that time answer like this, right? So we're giving it multiple examples, and that increases the chance that it will get the task right. It'll do what it needs to do, right? And another reasoning, and other kind of patterns that you can use is chain of thought or tree of thought reasoning, where you're teaching the model to think step by step, right? So we won't go into the details of this example. Essentially, it's just showing that standard prompting, if you give it a word problem, it might just get it wrong, and it won't give you any reasoning for that either. But if you give it a couple of examples where you are thinking step by step and then reasoning to arrive at the solution, it'll start doing the same thing, right? Because it's going to mimic the examples that you've given in the prompt. I think for models like ChatGPT, now it's just enough to say, let's think step by step. They've been tuned on that. So let's think step by step actually triggers this chain of thought also. So this is very important, where you want the model to reason through, and where you have a complex problem that you want it to think through in steps. So this becomes quite useful there. All right, and now getting to the last goal of adaptation, which is adding new knowledge. We do that through retrieval augmented generation. Some of you might be familiar with that technique already. Retrieval augmented generation basically is to augment your query. So you give a query to the LLM, right? And you expect it to give you a response back. In retrieval augmented generation, along with that query, you're giving it the data that's needed to answer that question, right? So you're basically saying, answer from this data that I'm giving you. The way the place where the whole RAG process starts is here at the vector database. So you've got your documents. Say these are your company documents, right? So your HR policies, for example. You chunk them, you create chunks, and then you embed those chunks into vectors, which are just numerical representations. And you put all of those in a database, right? So this database is now populated with numerical representations of your company data, right? You put in your query. When the user asks the question, the question will actually also get mapped to an embedding first, right? So a vector will be generated. And then that goes into the database to be matched against relevant documents. This is called semantic search. And semantic search has existed before LLMs also. Semantic search actually powers Google search. That's why Google search has got so much better. So semantic search is basically the whole vector mapping process. This is to enable semantic search. And this is basically so that the meaning of the query can be understood. So you're not just doing a simple keyword search anymore, right? You're actually taking the meaning into account. And then based on that search, it actually generates the top K, where K is a configurable parameter, most relevant documents, right? And it gives you a ranking. This is the most relevant, this is the second, this is the third, this is the fourth, right? And now the LLM takes your query as well as these documents into account when it's answering the question. And most of the time, we restrict it by saying something like only use the context to answer, if that's what we want, which is what we want most of the time, right? So it's going to be actually able to answer over your documents. And the cool thing about it is that this does not require any fine tuning. So you didn't go through any training. You didn't give it any training over your company documents. This just happened at inference time. So this is quite a powerful technique. This also minimizes hallucinations. Hallucinations is when the LLM makes up a very fake but very credible sounding answer, right? That's a common problem in LLMs. So you can force it to actually cite from the document, right? So that forces it to just stick to the facts and not hallucinate. So this is basic RAG.
When does the hallucination happen? अगर हम पिछले वाला जो distribution का chart है, fundamentally is it picking something that's not in that distribution chart?
It is picking something from the distribution chart, okay. But because it's not grounded in fact, right? Normal LLM operation is just that it's got this set of likely words, and it's going to just give you the next most likely word. So it knows how to stitch words together into a very sensible sounding response, but it's not grounded in fact. Normal LLM operation is not grounded in fact. Yes. Okay. So this is basically, RAG is just a grounding technique, like to ground the answer in fact, right, in part. So this is the basic RAG flow. This by itself might work for a lot of your use cases. And then there are a lot of ways to improve RAG, right? We don't have time to go into all of them. I do have this table here. I am happy to discuss this offline. This is basically like another whole talk in itself. But essentially, I'll just very quickly just tell you the basics. There are two things that you can improve. Either you can improve the query itself, because the user might not have asked the best possible worded query to match the most relevant documents. So you can ask an LLM for help in refining that query or expanding that query. And the second thing that you can improve is this relevance over here. That's the second main component, right? How relevant are the documents that are being retrieved? So you can add additional machine learning models here that you can train such that it gives you more relevant documents. So that's just the very high level idea. I think that's all we have time for to go into right now. But I'm happy to discuss later if anyone wants to. All right, so that brings us to the end of the adapt step in the LLM service deployment lifecycle. Next, we'll very quickly go over evaluation and deployment. So now you've adapted your LLM, right, to the best of your ability. Now you need to evaluate how well is it actually doing, right? So how do you evaluate that? The thing is, because this field, again, is relatively new, there aren't really standard sets of evaluation metrics like we have in other ML or NLP domains. So there are multiple options. Either you can borrow task-specific metrics from natural language programming, right? So for example, if you're doing summarization, very specifically, you can use something called the Root score, which will tell you how good of a summary is it. It'll give you a numeric output for how good the summary is. If you're doing translation, you can use the Blue score, which again gives you a numerical rating for how good the translation is. But again, these are very task-specific. So they'll work when you have these small specific tasks for which these metrics already make sense, but these are not very versatile. They're not going to work for all sorts of, I'm sure you can think of many tasks that are much more, for example, how do you evaluate the quality of a story? You probably can't do that with an existing NLP metric, right? So either you'll end up making your own task-specific metrics, or you'll use some standard metrics that are already there. These are very reliable, these are scalable, but they're not versatile. They won't work all the time, right? You'll have cases where they won't work. People use human evaluation. People have used human evaluation in the past. I believe that's how it started out. So people were just using humans to, getting humans to see how well the LLM is responding. Obviously, that's not very scalable, right? Even though that's very reliable. The recent trend is for LLM-based evaluation, where again, as we discussed in RLHF, you just replace the human with an LLM, right? So and LLMs have been shown to actually be very good at correcting their own errors, right? So if you even give the same LLM its completion again and say, how do you think, can you improve this for, I don't know, helpfulness or toxicity or something, it's actually going to do a pretty good job of doing that. Or you can use a different LLM. You can use a larger LLM or something, right? TrueLens already uses LLMs in their RAG evaluation, and they are being used currently in lots of other libraries also. So they're versatile, they're reliable, and they're much more scalable than humans. So that's probably the best option most of the time. Finally, for deployment, in deployment, we'll only talk about, obviously, any other deployment issues are pretty standard for any kind of web application, right? So we'll only talk about the fact that these models are very large, right? So they can be costly to host and to serve and for inference. So model optimization techniques should be used at this point to reduce that cost. You can reduce the size of the model either by pruning, which is where you remove the redundant parameters that are not adding value to your decisions. You can have the larger model act as a teacher and slowly train a smaller model, a student model, and then eventually replace the teacher, right? So it's like training the trainer kind of thing. That's model distillation. And the third is quantization, which is very simply you just take the weights of the model and represent them in a lower precision. So like if there are 32-bit floating point values, you represent it as 16-bit or 8-bit. So there's some loss of precision, some loss of performance, but it's been shown that it's not that bad, right? So you can do that to reduce the memory footprint. All right, so that brings us to the end of the LLM service development lifecycle. So now we've seen how you go from a use case to an LLM that's deployed and ready for production use, right? Now we'll get to the most exciting part of the talk, and this is much shorter, right? Here we talk about building GenAI agents, which is where the future and the real power of LLMs is. Now first, before we go into that, we've seen how we develop an LLM service, right? How do you go from there to an application? That's very simple, right? You just deploy the LLM in part as a service in your web application stack, right? Then you're good to go. So that makes, so basically that converts your LLM into an application, right? That's like probably ChatGPT. For ChatGPT, that would be enough, right? But can it really do almost anything that you want it to do at this point? It can, as long as it's a prompt completion, right? And as long as it's not math. LLMs are famously bad at math. Or it's not live data. LLMs are not able to look at live data, right? So there's still a lot of limitations. It can do prompt completions, sure. So if that's all you wanted it to do, and those prompt completions are of the type that the LLMs can do, you're good. But what if you want a more complex application where your LLMs are actually powering an autonomous agent that's actually also able to carry out actions? We didn't see anything about actions, right? We just saw that LLMs can talk to you. But they can't actually do things. They can't call functions. They can't call external tools, that sort of thing. So what if you want that? Some examples are maybe a customer service chatbot, which you want the chatbot to classify emails that it receives, even reply to emails, even route those emails to the right maybe department or the right person, right? That's a relatively simple example, but it involves some actions, right? A food delivery assistant that can suggest deals, that can track, execute, place an order, right? An information assistant that can search live data and summarize the information, visualize it, so on. If you think about these first two, actually all of them, they require the ability to not just talk to you, but to also trigger functions, to make API calls, to invoke external tools. So where does that fit in then? How does an LLM do that? So that's what we call a GenAI agent, right? So it's an agent that's actually empowered to take action. So LLMs are good at reasoning. They're good at understanding. They're good at language generation. But how do you bring in action, right? This is a rather complex workflow. I'll try to break it down for a GenAI agent, right? And this is pretty much a typical workflow that's being used in these agent sort of applications. You've got your user, I'll use the pointer. You've got your user, right, interacting with your application. So the user is just giving in prompts, just like we give to ChatGPT. But here in this whole, this yellow box, you've got the agent side of things. Now this agent is actually planning tasks based on that prompt. For example, I might say, I feel like eating some spicy food today. Can you order me something based on my preferences? Now that's a pretty complex thing for an LLM to break down, so it'll have to plan that task. It'll have to say, okay, it requires many steps, right? It requires looking at what I've ordered previously. It requires looking at what's available in my locality. It'll require looking at whether it's spicy, maybe looking at reviews, right? So it's going to plan that task and suggest the next action, which is basically going to go into your tool parser, right? So it's going to then figure out which tools do I need to carry out these actions. And then it's going to call those tools. These tools can be services, right? They can be microservices. They can be LLMs, they can be other agents even, right? Depending on what the action is. They can be other APIs, functions. And then when those tools give their output, then that output has to be interpreted. The agent has to decide whether the task is complete or more steps are needed. If more steps are needed, it'll go back into the loop. If it's done, then it'll generate a response to the user and say, your order for such and such has been placed, and so on, right? Or confirm or get user input or something. Now, where's LLMs here? At least in these portions, so 2, 3, 6, and 7, the task planner, the tool parser, the output interpreter, and the response generator, at least these will have LLMs. Possibly even in other places you could have LLMs, right? So LLM is basically, it's your reasoning agent, right? So it can be anywhere where you need reasoning, where you need language understanding, where you need certain types of output generation, right? There could be LLMs here. There could be other agents here in this portion. So, and this is not, this sounds very futuristic, but for anyone who's working in this domain, this is already possible, right? It's already possible. There are so many frameworks that can already enable this. There are countless. I've just given 2 over here, but there are so many, right? And they're all, new ones are coming out all the time. What a GenAI agent future might look like, which to the best of my knowledge does not exist right now.
Can we go by?
Yeah.
So what do you think? Can this be applied to a software development lifecycle?
It can. Because you have LLMs for doing...
Bad news.
So we need to do it. Yeah, it can be.
You will need different kind of ops. DevOps would be one very different. So now there is called LLM
ops, yes.
Because it incorporates a lot of different factors that build on top of DevOps to incorporate this kind of thing.
So we'll end here at an optimistic vision of the future. Scary to some. Yes. So here you have a reasoning agent. So you have an agent, a GenAI agent. The user is saying, look at the sky. Do you think it'll rain tomorrow? If so, give me an umbrella. And it's actually able to do all of that, right? Because we're assuming there are robots somewhere in the picture that are actually able to bring the umbrella as well. So you can see these are basically, just where I want to end is these are the agent, action, perception, brain. These are the typical components of an AI agent. This idea has been around for a long time, right? So it perceives the environment through some input sensors. It processes that in its brain, right? And it takes some action. And then that action impacts the environment. So the perception is obviously sensors. Lots of IoT stuff could be here. The brain is where the LLMs can basically serve as the brain, right? That's what people are saying now. So LLMs can serve as the brain of the agent because they're so good at reasoning. And then the action could be, again, LLMs, other agents, external services, robots, and so on. So this future could also be possible with GenAI. All right, thank you for bearing with me for a pretty dense, I think, talk. If you have any questions, I'm happy to answer. I'm not sure how much time we have.
But thank you. This was very useful.
Is it possible for AI to determine whether this specific response was generated by it? If we get for example, I get a text message or something from somebody and I paste it in ChatGPT and say, did you say that? What is?
I don't think that's possible right now. People do keep talking about it, but I don't think it's.
Context limit like thousands of
Yeah.
Is it not saving it somewhere or keeping it?
People do keep talking about this idea. I've read it at a very surface level, but I've never seen that it's actually possible to distinguish between. I haven't seen it personally. I do know that even conferences have this AI index now where they try to figure out if you use ChatGPT to write your paper. But I do know I have anecdotal evidence on this that it comes out very wrong. So I know somebody who wrote a paper by herself, right? And it was rejected because the AI index was very high. So I don't think they're very accurate right now. I think this is a challenge, one of the challenges.
But definitely asking ChatGPT is not the way they are doing an AI index is there some metrics over there.
Some metrics.
But the idea that I'll ask ChatGPT and tell that just completely it hallucinates at that.
Yeah.
Sometimes say yes, sometimes say no.
Because you think about it, we have to train it for everything, right? How do you train it for that? At least it hasn't been trained for that. Any other questions?
जब आप डिप्लॉयमेंट स्टेज पे थी और बात करें कि अगर हमने मॉडल की कॉस्ट को सेव करना है तो हम रिडंडेंट जो पैरामीटर्स होते हैं उनको रिमूव करते हैं तो अगर फॉर एग्जांपल एक मॉडल के 100 बिलियन पैरामीटर्स हैं तो आप उनमें से कैसे डिसाइड करेंगे कि ये पैरामीटर जो है वो मेरे स्पेसिफिक के लिए यूज़ केस के लिए रिलेटेड है तो चलिए मैं इसको रिमूव कर दूँ
इसकी हाँ इसकी बहुत सारी एडवांस टेक्निक्स हैं जिसमें we obviously didn't have time to go in and I haven't even gone into that much detail in all of them. There are several techniques. मतलब एक तो बहुत ही सिंपल है ना कि आप जो क्लोज टू जीरो वेट्स हैं उनको सिंपली रिमूव कर दो, लेकिन ऑब्वियसली वो हर वक्त नहीं होंगे या बहुत थोड़े होंगे तो दैट माइट नॉट मेक अ बिग इम्पैक्ट, बट देयर आर अदर टेक्निक्स. जैसे हम मशीन लर्निंग में फीचर इंजीनियरिंग करते हैं तो वी हैव टेक्निक्स टू डिटर्मिन कि ये फीचर्स इंपॉर्टेंट हैं, इसी तरह वी हैव सम टेक्निक्स टू डिटर्मिन कि कुछ पैरामीटर्स ज़्यादा इंपॉर्टेंट हैं.
Before we close off, एक YouTube पे एक question था about is there a model for improving testing, or is there a plan already? Does an LLM exist that is primed for testing?
For software
testing.
testing, I haven't personally explored that the area of GenAI as a as part of as software development life cycle के अंदर, but I do think things are coming up. I think एक दो हैं भी, but वो उनकी कितनी I think वो static ही है pretty much testing. This is what I know, but I have limited knowledge on this.
It's probably going to be trained to a particular use case. You have to give
Yeah.
them domain specific
Yeah.
data set for it to say it's not ready to
Yeah.
test cases.
Hmm.
Sure. Either somebody is building it or
Because the whole area of code assistance, LLMs, I mean, that is growing pretty fast. I'm pretty sure things are coming out, but I doubt that they're mature enough yet to.
So I'm a frequent user of ChatGPT, and I've noticed over time that the free version is giving more and more inaccurate responses. So my question was, are they doing that on purpose, or is it the human involvement factor that the free version is giving wrong answers?
Yeah, I'm not sure. It could be that factor because we are giving thumbs up, thumbs down feedback, and that might not be working out very well. It could be deliberate. I think that's not a.
But is there a way to deliberately make it inaccurate?
Of course there is. You can just train it like that. ये तो machine learning में हमेशा से मसला रहा है कि उसको आप slow poison कर सकते हैं. So it's just a machine learning model. You can poison it.
RLHF की बात हुई जैसा वो आपको
आपने
it doesn't allow you to say hate speech or give something. You know it's staged. You see just around there's this entire area of how do you hack through their jail.
Yeah.
There's a jail that is created.
Jailbreaking,
by
yeah.
These trained sort of prompts, and people think of innovative ways that how do you get your LLM to still give you the answer that it's not supposed to.
Yeah.
So human involvement is not encouraged.
होगी of course.
नहीं, ह्यूमन इन्वॉल्वमेंट हो सकती है. यू हैव टू बी यानी आप उसकी बात करें कि जो लाइव ह्यूमन फीडबैक है वो मॉडल को इम्पैक्ट करनी चाहिए या नहीं. यू हैव टू ऑलवेज डू दैट. दैट्स वो ऑनलाइन लर्निंग का एरिया है मशीन लर्निंग में, एंड यू हैव टू डू दैट केयरफुली. यू हैव टू काइंड ऑफ मे बी वेट द डेटा सेट, क्लीन द डेटा सेट टू मेक श्योर दैट इट्स नॉट गोइंग टुवर्ड्स स्लो पॉइजनिंग ऑफ द मॉडल, बिकॉज यू आर राइट, दैट्स ऑलवेज अ रिस्क विद ऑनलाइन लर्निंग. ऑलराइट, आई थिंक do we have time for one last question? Yeah.
Testing होना
So, आपके साथ so in terms of like the evaluation वगैरह है, इसके like मैं personally in terms of like testing perspective from the automation side काम कर रहा हूँ from like 6 to 7 months. उसमें जो मुझे like जैसा आपने कहा scalable है चीज़ को, तो जो मुझे issues में ये है कि like how to make it like in autonomous way, like मतलब अगर हमारे पास मिसाल के तौर पर डॉक्यूमेंट्स की मिसाल है, like specifically आपका डॉक्यूमेंट्स विद टाइम चेंज हुए जा रहे हैं और विद टाइम आप क्या कहते हैं डेटा सेट सारा चेंज हो रहा है. ओके, फॉर स्मॉलर स्केल आप कर सकते हैं कि दीज आर लाइक माय 5 to 10 डॉक्यूमेंट्स, और इसके बेस पे हम अपने कोई भी जो जिसका मैंने का वैल्यूएटर्स वगैरह यूज करके सारा रूल्स वगैरह सेट करके वैल्यूएशन करते हैं. बट इट इज स्केलेबल इस लेवल पे है कि हम लाइक उसको कर सकते हैं कि मतलब लाइक फ्यूचर में कोई भी चेंजेस आ रही है, पूरे डॉक्यूमेंट्स हमारे चेंज हो गए तो हमें कोई रीडू ना करना पड़े, हमारा वही सेटअप वैल्यूएशन दोबारा चल जाए. इन द सेंस कि लाइक अभी आप ये तो कर सकते हैं कि लाइक हम क्वेश्चंस भी कुछ जनरेट कर लें, ऑप्शन को आंसर भी कुछ जनरेट कर लें, बट उसमें मुझे ये लाइक जस्ट अ थॉट के लाइक ये तो फिर वही हो जाएगा कि आप एआई को ऐसे ही इवैल्यूएट कर लें. देन इन दैट केस आपका अपना मॉडल जो है जिसको आप टेस्ट करें उससे बेहतर होना चाहिए, व्हिच मोस्ट प्रोबब्ली नॉट द केस बिकॉज़ वो एक आपका प्रोडक्ट वाली साइड होगी और एक आपको टेस्टिंग. सो हाउ उस चीज को हम किस तरह कैटर कर सकते हैं?
ये completely it would depend on which evaluation metric I think you're talking about, because for example some evaluation metrics might involve some kind of मशीन लर्निंग, उस केस में आप रीट्रेन कर सकते हैं। जो आप AI से चेक करने की बात कर रहे हैं, एज आई सेड LLMs डू हैव द कैपेबिलिटी कि वो अपने रिस्पॉन्स को भी, जब आप उसको डबल चेक करने को कहते हो, तो अब क्योंकि वो एक डिफरेंट टास्क आपने उसको दिया है ना, तो वो समटाइम्स उसका ये नेसेसरी नहीं होता कि यू हैव टू यूज़ अ बेटर मॉडल टू इवेल्युएट योर मॉडल, यू कैन इवन यूज़ द सेम मॉडल। तो दैट वुड ऑटोमेटिकली बी डायनामिक, राइट, बिकॉज इट्स नाउ लुकिंग एट न्यू डेटा, तो वो उसकी बेसिस पे वो करेगा। But you can, yes. Yeah. So, but it would depend, metric to metric vary करेगा कि आप कैसे उसको scale करेंगे. All right. Thank you very much. Thank you for being here. That was very enjoyable.
Thank you so much. Let's thank